Hello everyone. I am Nicolas Ducros. I'm an assistant professor here at INSA Lyon and researcher with the Creatis laboratory. Welcome to this spring school. Hope you enjoy being here with us, at least virtually. If I'm not mistaken, this is the first lecture on deep learning for inverse problem. As you know, deep learning has revolutionized the field of computer vision, outperforming all other machine learning techniques for image recognition tasks such as object recognition, image classification, and segmentation. And aside from these tasks, it has recently become evident that deep learning networks are also powerful for image reconstruction tasks, and this is what we will discuss in this lecture. In this lecture, I will address the problem of reconstructing images, and I will also focus on the link between methods that are inspired by deep learning and traditional reconstruction algorithm. This is a current concern with deep learning reconstruction. It's referred to as explainability or interpretability. And obviously I will not able to review all the different network architectures that are interpretable or explainable. I will only focus on a few that have been designed in our team. In this lecture, I will start with basic introduction, and then I will focus on compressive optics. But the concepts I will introduce here applies to any basically linear inverse problem and to any noise model. So this is something quite general, and there will be a second lecture that will focus more on ultrasounds and computerized tomography. Okay, let's move to the second slide. Okay, so let's start this with images. So all those three images, so the first image here is a computerized tomography image. Here we have an ultrasound image, and here we have a magnetic resonance image. And those three images have a common feature. Those are reconstructed images. This means that those images have not been acquired directly. Obviously, here we have slices. So here we have a slice of the thorax of the patient. Here we have a slice of the brain of the patient, and we don't want to cut the patient into slices. So those images have been mathematically recovered from measurements that have been performed externally. And this is maybe why inverse problems are some of the most important mathematical problems in science, because they tell us about parameters that we cannot directly observe. So we do indirect measurements, and from those indirect measurements we try to recover quantities of interest that we cannot observe directly. In computerized tomography, in CT, here you can see we have an image. So we have an image that tells you about the X-ray attenuation of the tissues. And if we look at this thorax here image, we have okay, let's start with the table. So the patient lies on the table. So here's the table, and in white here we have the bones, and in gray we have the adipose tissue, fat tissue, water basically. And here what you can see is the lungs. Okay. And Inverse problems are not limited to medical imaging. They have wide application in many different fields, such as system identification, optics, radar, acoustics, communication theory, also importantly geophysics and oceanography. This is quite similar to medical imaging. We want to see something inside, so inside the earth, in the oceans, and to have access to this kind of information, we do measurements on, for instance, on the surface of the earth, and from that we want to recover what's inside. Okay, so now we can move to the next slide. Okay, so in this slide I will try to formalize a little bit what I've said before. Basically we have this equation here, m equals a of f, where m represents the external measurements that have been performed on the surface of the patient. F represents the internal quantity of interest. So this internal quantity of interest is actually the images I showed before. So in computerized tomography, this quantity of interest is the attenuation, X-ray attenuation of the tissues. In MRIs, it's related to the proton density. In ultrasounds, it's related to the density of the scatterers that scatter the mechanical wave. Now, in ultrasound, basically we shake a little bit the sample, and we have a wave propagating within the sample, and then it is scattered back by the scatterers that are present within the medium, and you detect that with a probe. Here A is the so-called forward model, so it links the quantity of interest F internal to the external measurements. So this one basically tells you about the physics of the image acquisition process. If we go back to computerized tomography, to CT, it tells you about how the X-ray photons and the sample interact, maybe through the photoelectric effect or scattering effect, and also it tells you about the measurement device itself. Okay. Now I'm gonna simplify a little bit this equation here, considering discrete linear problems. Most medical imaging problems are linear or can be considered as linear, which means that m directly equals a times f. And here I will consider a discrete setting, which means that f, the unknown f, is discrete, and actually it's a vector. It's a column vector with n pixels, with n entries in this vector, and the entries of this vector represents the pixel in the image. So here it's an image, it's two-dimensional, but we put all those pixels into this column vector f. And this is our unknown. A is the forward model, it's a matrix. M is the measurement vector. I'm gonna explain this and then I will go back to A. M is the measurement vector, it's a column vector, it has m entries. So for instance in CT, if we have a detector with a given number of pixels, and we observe the sample under a certain number of views, then the number of measurements, capital M here, is the number of pixels of the detector times the number of views. Okay, it's basically the number of measurements you acquired during the acquisition. And A, it's simply a matrix. So here we have a matrix with capital M rows and capital N columns. And if you want to simulate the measurements, you just multiply an image by F by matrix A and you get the measurements. Okay. So in this framework, what we want to do basically is to invert this linear system of equation, because we know M, we know A, and we want to recover F. Traditional approaches for image reconstruction minimize a cost function that has two terms. The first term is a data fidelity term here, and the second term is a regularization term. So let's have a look first at the data fidelity term. We said that we want to invert a linear system of equation, M equals AF. One way to do that is to minimize the difference between M and AF, AF being the measurements that are predicted for a particular image F. And if you minimize the difference between the two, then you will promote images that are hopefully close to the solution you are looking for. Unfortunately, this is not sufficient here, as A is badly conditioned. This means that an image F that is much different from the true solution can lead to the same measurements. Okay, this is due to the noise amplification that that can occur due to the poor conditioning of A. And the typical situation is to get an image F that has a lot of very large and very low values and that oscillates a lot. Okay. To avoid that, we add a second term to the cost function. This is this regularization term, and we try to design this to be small when the image satisfies some prior condition. So here we incorporate our prior knowledge about the solution. For instance, if you don't want an image with very high and very low value and that oscillates a lot, you can use this typical prior. So it's this L2 norm of the image squared. And this term will be small if the L2 norm is small. So if you have very high value and low values, this term will be large and you will discard this kind of solution. Another popular choice is the so-called total variation prior. As you can see here, it's the L1 norm of the gradient. So as we consider the gradient, we are looking at the variation of the image. We minimize this term, so we want that the image, we don't want that the image vary too much, and we have this L1 norm here in order to promote a sparse solution, that is solution in which you have a lot of zeros and only a few non-zero entries, and this kind of term promotes piecewise constant solution. You can minimize this cost function analytically. For instance, if you have a quadratic regularizer such as this one, but usually when you have more complicated, more advanced regularizers such as total variation, you have to minimize this cost function numerically using iterative algorithms, and this can be really time consuming. Now let's have a look at the deep reconstruction method. Deep reconstruction methods attempt to learn a mapping G such that this mapping directly provides the solution from the input M. So it's a mapping, you feed this network with M and it directly outputs the solution you're looking for. Here omega represents the network parameters. So this network, it's just parametric model with a lot of parameters. So you want to tune the parameters such that you can get directly out of the network an image that is close to the true image that has provided the measurement M. This requires two phases. So we have two phases when we work with deep reconstruction methods. The first phase is the training phase. In this training phase, we tune the parameters omega. To do so, we need a database. Here we need a pair of vectors, f, l, and fm, and you need a lot of them. So here typically you need L equals 10 to the 4, 10 to the 5, or even 10 to the 6 images. So let's say 100,000 images. And from those 100,000 images, you will try to find the best parameters. To do so, you optimize the loss. So typically this loss, it's the difference between the true image FL and the output of the network. So here the output of the network, okay, it's the same network as this one. I just here put the parameters of the network inside the parentheses, but it's exactly the same network. And omega here is the parameter we want to tune such that those two quantities are closed, which means that our network reconstructs actually the image F. And we minimize this loss over omega. So this is really important, and this is one of the main difference between the previous methods. In the previous methods, we optimized a loss function, but the loss function was a loss function where we optimize F directly. Here we do not optimize over F, we optimize over omega. And once we have trained omega, once we have optimized omega, then we will just reconstruct the image by using our network. Okay, we feed the network with M and it outputs the image. That's it. This training phase is typically slow, so it takes several hours or days, but its evaluation is fast. It usually takes 10 of milliseconds. Okay, and this is why deep reconstruction methods are also powerful. It's because they allow for real-time reconstruction. I'm gonna now briefly talk about compressive optics. So compared to a conventional imaging setup that directly image a scene, so here the scene is a mouse, compressive imaging setup usually acquires the image in a transform domain, as for instance a Fourier or Hadamard domain, and the raw data cannot be exploited as it is. The image has to be reconstructed, and this is where we need a reconstruction algorithm. A compressive setup is more complex than a conventional one. However, it can provide increased resolution or as in this example, give access to richer information content. So if you're in these examples, you can see that we have a spectral information here because we have two colors, and the red dots indicate the presence of a tumor, where in the conventional image we don't have the red dots because we image with just one color. I'm gonna now describe a computational optics problem that we are working on in our lab. This modality is called compressive single pixel camera, and it is very useful for hyperspectral imaging. So let me explain you how this acquisition setup works. We have Okay, the scene is here, so light goes in this way. The object will be here, and the image of the scene is reflected in a special light modulator, which is an array of micromirrors that can be tilted into two different states. In one state it will reflect light towards here an optical fibers, and in the other state it will not reflect it towards the optical fiber. And this optical fiber here is connected to a spectrophotometer that can measure the light spectrum. To perform an acquisition, we upload different patterns onto the special light modulator. So here white means that light will be reflected towards the optical fiber, and black means it will not. So we upload this pattern, we get a value here, we get a measurement here, we upload another pattern, we get another value here on the point spectrometer, and so on and so forth. And this is how we collect the raw data. Here I represented some values, but in reality it's what we measure are spectrum. So we measure different spectra for the different patterns, and from those raw measurements we can recover a hyperspectral cube that basically tells you gives an image with an extra dimension, and the extra dimension is here. So here you can see the image at 650 nanometers, and the image here at 459 nanometers. Okay, so you have a full hypercube. Okay, so let's see how this can be modeled. So here we still have M, or measurement vector. The patterns we upload, the light patterns we upload onto the DMD, we can put them all together in a matrix. That will be our forward model. So in my first slides, the forward model was denoted A. So here it's denoted P1. It's the light pattern we consider, and the image we are looking for is F. Okay, so now here I just have a model in which I consider not all the different wavelengths, but just one wavelength. So here we want to reconstruct one image F, okay, at one particular wavelength from the measurement at one particular wavelength. Okay. And here the P1 matrix has much more columns than rows, and it has much more columns than rows because we don't want to acquire a lot of measurements, because this takes time. And this is also something you have in other modalities. To limit the acquisition time, you want to limit the number of measurements. Okay, but you want to sacrifice the spatial resolution of the reconstruction. So this is where we have to be a bit smart when we do the reconstruction. Okay. So first question, how to choose the pattern. Second question, how to recover the image F. So this is a bit specific to the problem we are discussing here, but I'm going to mention it very briefly. This problem has been addressed by Jacques Hadamard, the French mathematician who made major contributions in number theory and partial differential equation. The solution is provided by the so-called Hadamard matrix. Those matrices are have only 1 and -1 entries, and they provide you with the best way to acquire an image and to reconstruct an image. Best in the sense with the best signal-to-noise ratio. Okay, so this can be illustrated here. If we consider noisy measurement, so what you measure is the true measurement plus some additive noise here with known variance sigma square. If you acquire each pixel independently, so if you acquire the first pixel, here first pixel is acquired, then second pixel, then third and fourth, you will end up with a variance on the reconstructed image, which is going to be sigma square. However, if you acquire with the Hadamard matrix, okay, you will have a reduction in the variance by a factor n. Okay, and this is illustrated here. So here you can see the different patterns that are uploaded onto the spatial light modulators. You can see the images that can be reconstructed for different acquisition times. The higher the acquisition time, the higher the signal to noise ratio. As you can see here, if you consider a short acquisition time, so high noise, you are not able to recover the image with the raster scan, while you are able to recover this image using the Hadamard scan. Our problem is the following. We want to invert this linear system M equals P1F, where P1 is the forward model. P1 actually represents the patterns that we acquired. Those patterns are taken from an orthogonal basis, such as the Hadamard basis, but the patterns denoted P2 are not acquired to save time. To invert this system, we can use the traditional reconstruction algorithm that I briefly presented at the beginning of this lecture. They optimize a cost function, or this can be also formalized as a constraint optimization, where we minimize a regularizer under the constraint that M equals P1F, and different kind of regularizers can be considered. In 2018, Higam and co-authors proposed to reconstruct the image using a neural network. So the neural network was very simple. It's depicted here. The input is the measurement vector. It's a column vector, and the output is an image f star. So this network has two stages. The first is a fully connected layer. The fully connected layer basically maps the measurements into the image space. Okay, and after that we have a series of convolutional layers that basically work in the image domain. The question is, and that worked quite well, but the question is how to choose the nonlinear models and how this relates to the traditional approaches. To understand this question, let's start from traditional reconstruction. In traditional reconstruction, we can minimize, as I said, a regularizer. That could be a least square. So if we regularize the least square regularizer such that M equals P1F, this particular problem has the following closed form solution. Very simple. You just multiply on the left M by P1 transpose. This works because P1 is P, the Hadamard basis is orthogonal. And this is perfectly equivalent to multiplying Y star by P transpose being the full basis. And Y star is a measurement vector in which we have M for the acquired measurements, and where we put 0 when we put zeros for the non-acquired coefficients. The question is, what about completing the missing value here by some relevant values, and what does relevant here means? To dig into this problem, let's have a look at the data. So to have a look at the data, we considered a lot of images taken from the SCL10 dataset. For each of them, we computed the Hadamard transform, and we plotted the coefficients of the Hadamard transform. And here I just plotted two different coefficients. So the Hadamard coefficient number 2 and the Hadamard coefficient number 7, and here on this scatter plot each dot is an image. So this point is an image, this point is an image, this point is an image. Okay, and what you can basically see here is that those two coefficients are correlated. This means that if you measure 20 for Hadamard coefficient number 2, then it's very likely that coefficient number 7 equals -2, but it's very unlikely that coefficient 7 is -20. The completion approach consists in completing the missing measurement with relevant value y2 star before multiplying on the left hand side of the completed measurement vector by the full Hadamard basis P. We need to estimate those missing coefficients. To do so, we compute the following conditional expectation. This basically tells you the mean value of the missing coefficient from the acquired coefficient. Under Gaussian assumptions, we have an analytical formula for this conditional expectation, and actually it corresponds to the minimum mean-square estimator. This is given by, here we have m minus mu1. Mu1 is the mean of the acquired coefficient, so we center the acquired coefficient. We divide by the covariance of the measurement. We multiply by the covariance between the measured and missing coefficient, and we add the mean of the missing coefficients. Okay. If the Gaussian assumptions are not met, then this is still the best linear solution in this sense. Okay. So we proposed first to use this analytical solution to for the fully connected that is used in the deep reconstruction network. Okay. Here we have a lot of parameters. For instance, in this example, we had 1 million parameters in these fully connected layers and only 4,000 parameters in the convolutional layers. So the idea here is to freeze those weights so as to behave as the best linear solution you can have for your problem, and then only train these 4,000 parameters. So here is the Gaussian completion step that I described in the previous slide, and here we will learn how to compensate for the non-Gaussianities of the problem. If the Gaussian assumption was perfectly correct, just this fully connected layer would provide the best solution. But as in practice this assumption is unmet, then we have to compensate for the non-Gaussianities, and this is what those layers do. Here, so we compare the different approaches. So we have the free fully connected layer as proposed in the original paper, 2018 paper. We have the pseudo-inverse one, in which we just multiply by P1 transpose. So this is what you have with a completing the missing measurements by 0, and the Bayesian completion scheme I just talked about, and this is what we compare here. What we can say here is that the freenet has a lot of parameters to learn, while the PINV-net and the completion net have only 4,000 parameters to train. So here we have a look at the loss. Okay, so basically this loss, it's the mean reconstruction error over the training database. So what you can basically see is that here we have the freenet, so we train the fully connected layer. It's here, it goes down here. Here we have the completion net. Okay, so basically in the end the reconstruction error after 60 epoch is the same. Completion net and freenet have the same error. It's much better than the PINV-net. However, the completion net has less parameter to train. In this figure, we illustrate the peak signal-to-noise ratio for the reconstruction of all the test images in the STL10 database. So we consider the three networks described in the previous slide: PNFnet, CompletionNet, and FreeNet. And we also consider the pseudo-inverse solution and the completion with the conditional expectation. The highest peak signal-to-noise ratio is achieved by the completion network, which slightly outperforms the free network and the pseudo-inverse network here. Compared to the free network, the completion network has no fully connected layer to train, and hence it has a lot fewer parameters to train. In this figure, we consider a fluorescence microscopy image of melanoma cells in green migrating on blood vessel surface, here in red. We obtain an improved peak signal-to-noise ratio with the proposed completion network. So here we have the proposed completion network compared to the pseudo-inverse network. So the pseudo-inverse network is here. You have this staircase A-phase, which is due to the fact that we consider Hadamard patterns, and some of them are missing. And an improved PSNR over the total variation solution, which is represented here. And here I report the improvement in dB for the red channel and the green channel. Each channel here has been processed independently. The next question is, does it work with experimental data? Okay, so let's have a look at it. Here we have the grand tooth image. So this is an image acquired with all the different light patterns for long acquisition times, meaning for low noise. This is the reconstruction we obtain. No completion here, so pseudo-inverse solution, statistical completion, and the completion network. So this may not work because we are considering an image that was not included in the STL10 dataset. So to test this hypothesis, we also acquired an image from the STL10 dataset, and this is what we obtain. Once again, pseudo-inverse, statistical completion, and completion network. And as you can see, the results are not very good. And in terms of PSNR, for instance, the completion network is not performing very well, and probably the best performing method is the pseudo-inverse solution, which is a bit disappointing. So does it mean that the previous method doesn't work at all? So to answer the question, we have to go back to the scatter plot I presented you a few slides before. Our method basically look at the conditional expectancy, meaning that we acquire a coefficient, and from the value of the coefficient, knowing the correlation between the coefficient, we replace the missing coefficients by the mean value of the missing measurement. However, in the presence of noise, we have a deviation here in the measured coefficient. So we were supposed to measure -10, and we measure 0. Measuring 0, we will complete not by -8, but we will complete by 0. And this is a big issue here. So we cannot just apply directly the previous method. We have to take the noise into account. To solve the noise issue, we will update the previous approach. We keep the same model for the data, so we assume that the data is the measurement vector is the realization of a Gaussian distribution, and we will add a noise model. This noise model is related to the condition variable m, the measurement, given the noiseless coefficient. So if you know your measurement, you will be able to predict statistically the noisy measurement from the noiseless measurement. And then we will update our conditional expectation optimization, and we will consider not only the estimation of the missing coefficient y2, but also the estimation of the noiseless coefficient y1. If we do so, we have the following solution, which can be written into two steps. I'm gonna start with the second step. The second step, you will recognize it, it's the completion step. So you basically have this division by the covariance of the measurement, multiplication by the covariance between acquired and missing coefficient. You apply this not to the measurement themselves, but to y1 star. 1y star is a denoised version of the measurement, and it is given by this first step. This first step here is very similar to the second step. We center the measurement, so m alpha are the measurement, the actual measurements, the noisy measurements. We divide by this covariance, which includes the noise covariance and the covariance due to the data, multiply by the covariance of the data, and this is it. So this step is basically a Tikhonov linear filter. This we can plug these two steps into our deep completion network. So you will recognize the previous network, okay, with the post-processing convolutional layers in the image domain, the completion step in the data domain that can be implemented as a fully connected layer, and we'll have another fully connected layer here that will act on the acquired coefficient. Now I'm going to talk about Poisson noise. Poisson noise is difficult. It's not only difficult because we have no analytical formula for the completion problem. It's also difficult because the noise level depends on the image intensity, that is denoted alpha here, and we don't know this image intensity because we don't know the image. We want to reconstruct the image, which includes the intensity of the image, and this complicates things a lot. First problem, this scaling, which is unknown, is incompatible with nonlinear reconstructor. Why? Because if you have a linear reconstructor, if you reconstruct something just by multiplying by a matrix, then you don't care about the units of the measurements. Okay, if you have twice the measurements, you will get twice the reconstruction. But if you have a nonlinear reconstructor, such as a deep network, if you have twice the measurements, you won't have twice the results. You will have a completely different results because you have nonlinear steps in a deep network. This requires the data to be normalized. This is what we do here. It's gonna be here a bit technical, but it's really important to understand this if you face Poisson noise, a more generally multiplicative noise. So we have to divide here the measurements by alpha. Alpha is unknown at the reconstruction time, so we'll have at some point to estimate alpha from the data itself, to normalize like this, to plug this distribution into our equations, and then run our deep reconstruction algorithm. The third problem is that it does not satisfy the Gaussian assumption. So this is also an issue, but it's not a big issue because this we have quite good Gaussian assumptions at counts that are higher than let's say 20. So but we will take this into account. Okay, there we go. So the approximate noise model for the normalized data is going to be the following. So we approximate Poisson noise by a Gaussian with mean y1, and the covariance here is directly given as y1 divided by alpha. Why do we divide by alpha? Because we normalize the measurement. Okay. Otherwise you would have got here directly y1. I already mentioned that the covariance, which depends on alpha, depends on the intensity of the image, which is unknown, but we will estimate this from the raw data. Here's the training pipeline of the full network. So first of all, I would like to underline the fact that the reconstruction part of the network is only the right-hand part here. So in this part, we have here the measurement vector, the noisy measurement vector, M alpha. We have the reconstruction stage of the network, which outputs an image. Okay, but this is only the reconstruction stage. On the full network, we have two other stages. One here is the rescaling stage, which basically divides the measurement vector M by the image intensity, which is unknown but that we can estimate, and this estimation is denoted alpha tilde. And the first stage is the simulation of the measurement from the image F. As most databases are image databases, we start from an image database and we have a measurement stage here which simulates the physics, basically the forward problem, leading to M alpha. Then we rescale, then reconstruct. This is the full network. Something important here I would like to underline is the fact that to be robust to noise, you have to train the network and the varying noise levels. This is why here we consider alpha as a sample from a Gaussian distribution. So alpha, once again, is the image intensity. So we will consider image intensities with mean mu alpha, let's say 1000 photons, okay, and with variance here sigma squared alpha. So this is the variance of the image intensity. The image intensity is related to the noise, so sigma alpha is the variance of the noise, the variance of the noise. Yes. Okay. So we will train this network like this. Database, simulate the measurements, normalization, reconstruction. Okay. Now let me show you some experimental results. So you will recognize these images. So here we have the ground truth acquired in low noise conditions with a lot of light patterns, a lot of measurements. This is the image reconstructed by the completion network here. Here the image reconstructed by the completion network that was trained with noise. Okay, because this completion network, the previous one, was trained without noise, so you can see clear improvement when you train it with noise. And this is the denoised completion network that was trained with noise. Okay, so you can have a look at the peak signal to noise ratio. The higher the better. So the best peak signal to noise ratio is provided by the denoised completion network, and you can also have a look at the visual differences between the three networks. Here on the bottom row we have, you can recognize this STL cat, ground truth is here, completion network is here, a lot of artifacts. Here the completion network trained with noise, so as you can see there's a clear improvement, which means that training it with noise, even if it has no denoising completion in it, helps to implicitly learn how to denoise noise. So here you only act on the layers that act in the image domain, but you can clearly improve the reconstruction by training it with noise. And here it's the denoise completion network that was also trained with noise. So you can see that there's an improvement also here in the peak signal to noise ratio. Last result here, the so-called star sector. Ground truth image is here, completion network here, completion network trained with noise is here, and denoise completion network is here. So here again, the best result is obtained with the denoise completion network, meaning the network with both the completion stage and the denoised stage. I'm not gonna show results on this, but this is also something important I want to mention, is that when you don't know, in practice you don't know the noise level, so you have to guess what is going to be the noise level, and this is something really important. And we also observed that the denoise completion network is much better than the completion network trained with noise. I mean, this one is trained with noise, but it has no denoising stage, which means that it learns how to denoise the data, but implicitly. So when you do it explicitly, the resulting network is much more robust to different noise levels, while this network may completely fail if trained with one noise level and evaluated with a completely different noise level. Okay, so this is another advantage of the denoised completion network. Okay, this is it. Last slide on this part about the limitations of this approach. As you have probably noticed, the processings here are sequential, meaning that we do some processing in the measurement domain, namely denoising followed by completion, and then we do some processing in the image domain. And this has some intrinsic limitations. The first question is still the interpretation of the solution, okay, with the processing in the measurement domain, in which we do denoising, completion. We know that this f tilde here is the best linear solution in the sense of the minimum mean square problem. However, we don't know what is going on here in this image domain, where we have some convolutional layers, units, or any kind of networks. So there's still the problem of explainability, interpretability of the solution f star. A related question is the consistency of the solution. I mean, we don't know if f star is consistent with the solution. It may happen that if you simulate the measurements that would have been obtained with this S star, so building P1 times F star, this significantly deviates from the actual measurement M. Okay, so you have M minus P1 F star squared, that is larger than this epsilon here quantity that refers to the noise level. In this case, we say that Here in this case, if it's lower than epsilon, the measurements are the solution is consistent, but if it's larger, the solution may not be consistent with the measurement, which would be a problem. And also we have a link with solutions, traditional solutions obtained with traditional reconstruction algorithms, but there are also iterative reconstructions, iterative reconstruction schemes that solves this kind of problem iteratively, and it would be nice to also have to make a link between those iterative algorithms and our deep learning inspired reconstruction schemes. Iterative schemes may solve the previous problems. Iterative schemes may solve the problems I've just mentioned. Iterative schemes are deep reconstruction networks in which processing in the data domain and in the image domain alternates, as represented here in this diagram. So here we have the measurement vector. Okay, it is processed by some neural network layers, fully connected, convolutional, whatever. This outputs an image, and this image, as well as the measurement vector, serve as the input of another set of layers which outputs an image, and so on and so forth. And because we used several times the measurement vector, we will be able to check the consistency of the solution. If a solution is not consistent, we will if an image is not consistent with the measurement vector, we will see it. This kind of architecture also nicely connects with traditional algorithms that solve iteratively cost function with nonlinear regularizers. There are many variants of such algorithms. In particular, we will consider the deep expectation maximization network, which is a simple architecture that just loop over the architecture that we previously discussed. It's very simple and it has a theoretical foundation. I'm gonna talk now about those theoretical foundation. To do so, I will start with the expectation maximization algorithm. The expectation maximization algorithm is an iterative algorithm that is commonly used to find the maximum a posteriori estimate of parameters in a statistical model. So here we have the discussed function here, where P is the probability density function here of M, the measurement given the image. So this is the, let's say, probability of getting M when the underlying image is F, plus here this term that depends only on the probability density function of F. This term is well known because we already assume that this condition distribution is a Gaussian with known mean P1F and with known variance sigma alpha, so we know this term. However, the second term completely depends on F and is unknown. As a reminder, I mean, starting from the ground truth image here, if we consider the Gaussian prior here, we end up with the, we call it previously the pseudo-inverse, the Gaussian inversion here, and the Laplace, the total variation image here, if we use a Laplace distribution for F. In practice, the distribution of F is unknown, so we will have to learn it in some way. The expectation maximization algorithm requires to create an image sequence which solves these two equations here. I will spare you the boring details, but what you can see here is that you have two different equations. The first equations provides a solution here x bar that is injected into the second equation here, and this variable here is the so-called latent variable. It is in the measurement space because you compare it to PF, so it lies in the measurement space. And this is the a measurement you haven't access to, but you would like to compare to your previsions. Another remark here is that we have here in this equation the probability density function of f, so this term here is unknown. Okay, so we don't really know about this. In these two equations we have introduced the noise model that I described in the previous slide. The noise model is in here. Okay, so we have used this hypothesis, but we are still left with this unknown probability density function of f. This is why we rewrite this a little bit. So we keep the first equation and we will have an analytical solution for the first equation, and I think you will recognize it. And as we will not be able to solve the second or to go further analytically, we proposed to learn it. So here D is a network, and as you can see here, this network acts in the image domain. Here x bar, which is in the measurement domain, is multiplied on the left hand side by p transpose. So this quantity p transpose x bar is in the image domain, and we will have here a network that we will learn to provide the solution of this minimization problem, from which we have a term that is unknown. Okay, I think this is all what we need to know about this. So let's go to the next slide. Okay, if we go a little bit further into the equation, and in particular if we solve analytically the first optimization problem, which is basically quadratic optimization problem, we will get the following steps. So let's have a look at those steps. So we recognize the first two steps that are in the measurement domain, which are the denoising here. We have a denoising step here. We have m alpha minus, so this term is new. So far we haven't considered this term, so you could assume here f0, the first iterate is 0, and you will just get what we had before. Okay, so this is a denoising step. Then we have a completion step. So after denoising, we complete the measurement. So here, this y2 represents the missing measurements. Then this step is basically an update. So we take into account the previous estimate. Okay, we will see in a second how we compute it. The previous estimate, and you update it. You update it from the completed denoised and completed measurement yk. Yk consists is the concatenation of y1 and y2k that we multiply on the left hand side by p transpose. So this is something that lies in the object domain, and we add here this estimate. This estimate, we compute it by denoising, so it's a network. I call it denoising network. It's in the image domain network. It's in the image domain, and from f tilde we can compute fk. Okay, So now if we look at the diagram, we have M, the measurement, with denoise the measurement, complete the measurement, outputs an image, okay, by multiplication of P transpose. Then we go into we're in the image domain, we denoise in the image domain, so we have this network here, and then we update, okay, and this is it. Okay, let's have a look at the results. So here, simulation results. We have a ground truth image here, reconstruction using a unit only, so only a unit, okay, only a unit, no iteration, just a unit. Here we have the so-called model network. It's a model-based deep learning network, which is basically an unrolled network that was proposed for magnetic resonance imaging. And this is the proposed network, so as you can see it compares nicely with the other two approaches. Now some experimental results. So we applied the same network to experimental results, so you can see the results here visually. So on the first row you can recognize this image. Actually I haven't said, but this image here was the LED lamp that we used to illuminate the sample directly. So we have those big spots here. The pseudo-inverse reconstruction is here. Just unit directly is here. The model is here, and the proposed network is here. So you can see that an improvement in terms of peak signal to noise ratio, and here you recognize the STL cat. Pseudo-inverse image is here, quite blurry, and unit here, model and proposed approach was the one with the best signal to noise ratio. In conclusion, we describe deep reconstruction networks that can be interpreted as traditional algorithms in a Bayesian framework. The networks can be depicted as in this diagram. The measurement vector is processed in the measurement domain by two different kind of processing. We have a denoising step, then which is followed by a completion step. Then we map this into the image domain, where we apply a second type of In conclusion, we described several deep reconstruction networks that can be interpreted as traditional algorithms in a Bayesian setting. The first can be represented by this diagram. We have two different kind of processing, one in the measurement domain, the other one in the image domain. The measurement vector M is first denoised and completed. The measurement missing are completing, and then the resulting completed measurement vector is mapped onto the image domain. This part is interpretable and it hasn't to be learned. It is followed by a second step in the image domain, when we have usually convolutional layers that are learned during the training. This deep completion network can be interpreted as the conditional mean. Another architecture was described. It basically loops over the first architecture, and it can be interpreted as a deep expectation maximization network. Something very important is the training. I could have insisted more on that. I will do it now, but training is very important, in particular as in typical image reconstruction problems you don't know the noise level, you have to train the network with different noise level in order to get a network that is robust to different noise level. This is one of the main problem with deep reconstruction algorithms, and the interpretable network architecture that we discuss are in particular quite robust to unseen noise levels, which is one of their key features. We provide open source code. First of all, we provide code in MATLAB for the statistical completion. It is part of the single pixel image reconstruction toolbox SPyRiT. We also provide code in Python. It is part of the SPyRiT toolbox, so the single pixel image reconstruction toolbox in Python. In particular, we provide a Python package where we implement the traditional and deep reconstruction algorithms that we discussed in this lecture. We also provide Python scripts for traditional and deep reconstruction. The main Python package is on GitHub in the OpenSPyRiT organization, OpenSPyRiT/SPyRiT. The scripts are provided in the OpenSPyRiT organization under OpenSPyRiT SPyRiT examples, and among those examples you will find you will find a notebook that we will have a look at it tomorrow, not tomorrow, actually today, or tomorrow, depending on which session you attend. You will find a notebook in this SPyRiT example folder. I would like to acknowledge all the different persons who contributed to this work, and see you at the hands-on session. Have a good day.